In section 4.7, we're ready to talk about complex numbers. Complex numbers are going to have the imaginary component I, which is defined as the square root of -1. A complex number is going to be of the form a plus bi, and we're going to use the discriminant, which is the b squared minus 4ac term, as part of the quadratic formula to determine if some of our solutions are going to be complex. Then we're going to solve quadratic equations that have complex numbered solutions and be able to look at a quadratic equation and its discriminant to determine the types of solutions to some quadratic equations. All right, so this is where all of our practice in using the quadratic formula and simplifying it to get simplified solutions will come in handy, because when we're looking in the complex number system, these are not going to be graphical. So looking at this equation right here, this is y equals 2x squared plus x plus 5. Based on what we know about parabolas, will this function have any x-intercepts? And the answer is no, because it faces upwards, it's above the x-axis, it's always above the x-axis, it will never cross the x-axis. So it faces up with a positive vertex. So it never crosses the x-axis. Okay, so what can you say about solutions to the equation 2x squared plus x equals 0? So there are going to be no real solutions. We might have previously said there would be no solutions, but we're going to emphasize the word real here. There are no real solutions. There are complex solutions, but there are no real solutions. Real solutions can be seen in the graph. This one doesn't have any, but it is going to have some complex solutions. Okay, so we're going to use the quadratic formula to attempt to solve this. All right, so x equals negative b, so that's negative, I'll write down a and b. A is 2, b is 1, c is 5. It's already equal to 0, so I can use the numbers a, b, and c from the coefficients there. So negative b is going to be -1 plus or minus the square root of b squared. So that's 1 squared minus 4 times a is 2 times c is 5 over 2 times a, so 2 times 2. So I have -1 plus or minus the square root of, and we're going to simplify all the values that are inside of the radical, not the radical itself. So if we simplify the 1 squared minus 4 times 2 times 5, that gives us a -39 inside of our radical. And then we have -1 plus or minus the square root of -39 over 4. So right now it says use the quadratic formula to solve this. Where does the solution process break down? So the solution process breaks down right here because there is a negative inside the square root. Or radical is another word for the square root symbol. There's a negative inside the radical or the square root symbol. The radical is the name for that symbol. Negative inside the radical. Okay. So if we did try to evaluate the square root of -39 on a calculator or decimals, we would get undefined. So undefined doesn't work. So we are going to have to think about it in terms of the imaginary unit. Okay, so this is the one and only place that calculators can do things a little bit differently. Calculators have a complex mode where you can switch things in and get them to come out with the I value. It's not super useful because we don't really want to know the decimal version of this most often. We're not going to be able to do this on decimals. It does not have an imaginary mode because it's a graphing device, and you can't graph things that are not real or not that are imaginary. So what we would like to note for ourselves is that we're going to use the imaginary unit I. If we take the square root of -1, we use I for this. And this number is going to be complex. So if I did need to approximate the square root of -39 on decimals, I could take off the negative and say that this number, square root of -39, is 6.2429, etc. I. So I can get that value using decimals by taking out the square root. So the square root of negative 39 is the same thing as the square root of 39i, knowing that the square root of the negative 1 is I. And then if I did want the decimal, I could get it. Often I don't care about the decimal. But I could get it if I had to, just to talk about that. Okay? So, uh, and this is one example of a complex number. Complex numbers always have an imaginary component. Well, not always, but complex numbers can have an imaginary component. This one is a pure imaginary number because it does not have a real component added to the complex component. We'll look at the definition down at the bottom to talk about complex numbers. Okay, so the solution to this one, like I was saying, we don't often want the decimal for it. We would just say that the solution is the square root of 39 times I, or that's often reordered as I square root of 39, and that would be the solution. The solution is I. Well, no, that's just part of the solution. So the full solution for us, because it was, did they solve this one again later? Nope. Okay, so the full solution for this one would have been x equals negative 1 plus or minus the I square root of 39 over 4, and so on. So that's just the one part of it, the one component of the solution. And technically, while we're on the go of the solution, we would have to separate this to negative 1 over 4 plus or minus the I squared of 39 over 4. Separate the denominator into two pieces because that's in true complex number form. This is in A plus or minus BI form. So we'll talk about that again at the bottom of the page, but in case you're curious, that's how I would write the answer to number 2. They probably have me do number 2 again somewhere. I just don't see it. So I'll assume they don't. Okay, so now we're going to do some practice on not full quadratics. Those are going to come a little bit later, but just rewriting these partial quadratics, these radicals, these radicals that have a negative value inside of them. Okay, so the first one, the square root of negative 26, this is the same thing as the square root of 26 times I. Now, every time we simplify a radical, we should be asking if any perfect squares, like 4 or 9 or 16 or 25, etc., will go into the number. If they do, then you would want to break it down and pull out your perfect square factor as well as the I. But nothing goes into 26. Well, I mean, 2 and 13 go into 26. However, 4, 9, 16, those guys don't. So we're going to leave this as a square root of 26 times I. It's done. Okay. Then for the next one, the I will come out. Those will be the square root of 5 times I. Make sure that your I is not underneath your radical sign because that means something entirely different. You do not want your I underneath the radical sign. So sometimes that's one of the reasons that they will reorder it just to make sure it's extra clear that the I is not in the radical. Make sure your radical bar does not go too long and cover the I. It needs to not be in it. And if you're typing it, you need to exit the radical before typing the letter I. Okay. Now in the next one, this is the square root of 64 times I, but I know the square root of 64. The square root of 64 is 8. So this one would simplify to 8I. So these ones were done up here because I was not able to evaluate the square root. But when I get to the square root of 64, I can, of course, evaluate that as 8. The square root of 64 is 8, so I have 8I. Okay, now this one here, not yet simplified. I could multiply those together and get the square root of negative 21. So this is going to be the square root of 21I. And then for my 18, this is going to be the square root of 18I. And hang on a second, I am not done with the square root of 18I, unlike the square root of 21I, because no perfect square goes into 21. 3 and 7 do, but they're not on my perfect squares list. But in the case of 18, 9 goes into 18, and 9 is a perfect square. So I'm going to separate this into 9 times 2, and then I can do the square root of the 9 piece of it, right? So the square root of 9 is 3. That's out of the square root now because I've done the square root of 9, times the square root of 2, the part I haven't done, times I. So this one would simplify as 3 square roots of 2I. Okay, you can check it a little bit. You can't type the negative or the I in, but you can still see that the square root of 18 and 3 times the square root of 2 have the same value. So you can check the 18 portion of this has been simplified correctly into 3 square root of 2, and then the negative portion is your I at the end. That part you can't check, but you don't need to because you know a negative inside of a radical, a negative inside a square root specifically, is going to turn into an I. Okay. Continuing on, letter F is going to be similar to letter E. I would start this one off with the square root of 27 and I, and then I would think, I know that 9 goes into 27. So I would write this as the square root of 9 times 3 and I, and then I know that the square root of 9 is 3, and I can't do the square root of regular 3, so I'm going to end up with 3 square root of 3I. All right, 2 more. This one right here, this is the square root of 3/4 I. And then I can do the square root of the 4. So I'm going to separate the square root into the square root of the top and the bottom. Square root of 3 over square root of 4 I. And then I can do the square root of 4. The square root of 4 is 2, right? So this will be the square root of 3 over 2 I. So if there's a fraction, it's completely possible to be able to take the square root of either the top or of the bottom separate without, doing both. You don't have to do both. Okay, you can do the square root of the bottom in this case, so do it. In the next one, there's a couple of ways to go about this one. I noticed that my 27 is trouble, like it was up here, because I could break it down. But I also noticed that the 15 in the 27 is not a reduced fraction. So I can go either route on this. And what I would like to do on this one is probably reduce the fraction first, so I don't have any issues with that. So I would reduce my fraction. I can divide them both by 3. That's going to be 5/9. I'm going to go ahead and pull that negative out as an I right away. And then I can separate this to the square root of 5 over, I already know the square root of 9. The square root of 9 is 3I. So it's similar to letter G once I get the fraction reduced. Okay, so definition at the bottom, numbers that are every single one of these. Numbers that are of the form b times I, something times I, they're called pure imaginary numbers. They're numbers that are something times I, whether it's square root of 26 times I or square root of 5 over 3 times I. Those are pure imaginary numbers. Complex numbers are of the form a plus or minus bi, and those have a real number added on to an imaginary number. Now, in the case of complex numbers, a or b could be 0, so the pure imaginaries are complex, and so are all real numbers. They're also called complex. Complex is the broader bucket for the pure imaginaries, the reals, and the blends of the two. Okay. Onward. Okay, so some properties of imaginary numbers. One of them is that since I is defined to be the square root of -1, if you square I, you have the square root of -1 squared. And we know that squaring and squares are inverses of each other. So that means that I squared is going to be back to -1. Okay, so that's the property that they're showing us right here. That I squared is going to be equal to -1. Okay, so we'll keep that in mind as we go to the next page. We're going to do some operations on complex numbers. First of all, we're going to add, then subtract, then do some multiplication. When you're adding, it's all about adding like terms. So if I'm going to add up the two complex numbers, 3 plus 4i and -5 plus 6i, it's the same thing as adding 3 plus 4x and -5 plus 6x. You add up the like terms with each other. So we'll start with the 3 plus the -5. The two real parts are going to add up to -2. 3 plus -5 is -2. And then 4i plus 6i, 4i plus 6i is 10i. Okay, that's the sum of those two complex numbers. Now we're going to do the subtraction. So when you do subtraction, you know that the negative has to distribute. I didn't worry about distributing in the positive because a positive does not change the sign of anything. So the negative stays negative, the positive stays positive, and I just add. But here I'm going to distribute. So we'll have 5 minus 7i, and then two negatives make this plus 2 and a minus 5i. And then if I add up my like terms, I'm going to have 7 for the real component. 5 plus 2 is 7. And then -7i minus 5i is going to be -12i. So that's going to be our solution here. And now we're going to distribute again when we get to the multiplication. This is a monomial distribute. So we're going to take 5i times 2, that's going to be 10i. And then 5i times 4i is going to be 20i squared. Now, if I was doing a polynomial distribute, if I had 10x minus 20x squared, I would have been done. But I'm not done here because remember that I squared is a number and it is equal to -1. So I'm going to replace this with -1. So here I have 10i minus 20 times -1. And so that is 10i plus 20. And when you write a complex number, you write the real part first. So we're going to put the 20 first, then plus the 10i. And that will be our simplified answer, our number that is the result of that product. In part D, when I have to multiply two binomials together, I'm going to use all 4 parts of my product, or if you'd like to do the box method for distributing, you can do the box method for distributing complex numbers also. I'm going to do the 4 parts of the product. So 3 times 4 is 12, and then 3 times 5i is 15i. That finishes 3's job. It got multiplied by both the 4 and the 5i. Now we're going to take -2 times both of them. -2i times 4 is -8i, and -2i times 5i is -10i squared. So we're going to combine like terms. We're going to have our 12. We have 15i minus 8i. That's going to give us plus 7i. Then we know that I squared is -1. That's going to give us minus 10 times -1, or plus 10. And if I think about that plus 10, I have tons of room right here. -10 times -1 is a positive 10. Positive 10 plus 12 is going to be 22 plus 7i, and that would be our final answer. Okay, our next topic in this section is talking about the discriminant. The discriminant is the name for the stuff that is inside the radical. Not the radical itself, but just the stuff inside the radical in the quadratic formula. So it's the b squared minus 4ac piece. So we're going to look at these quadratic functions and determine just the sign of the discriminant. So I don't need anything else, just the discriminant, not the rest of the quadratic formula for these. Okay, so in the first one, the discriminant. So b squared minus 4ac, that's -7 squared minus 4 times 2 times -4. So that's 49 plus 32. And again, it doesn't actually want me to figure out what the discriminant is. It just wants us to figure out what the sign of the discriminant is. So that's some positive stuff. 49 plus 32 is a positive number. So when my discriminant is a positive number, that means that I'm not going to have a complex solution. I'm going to have a real solution. Okay, so we're going to take a look at this picture. Just go ahead and make a new one. Y equals 2x squared minus 7x minus 4. So you can see from the picture that you have 2x intercepts. Okay, so I'm going to draw my picture. Better put my x-axis and my y-axis right here. And it's something like that. But what I can see from this is that I have 2 x-intercepts. Okay, so if the discriminant came out positive, I have 2 x-intercepts. Let's see what's going to happen in the next one. Okay, so the discriminant, the b squared minus 4ac piece, b is 1. 1 squared minus 4 times 3 times 1. Okay, so that's 1 minus 12. Again, 1 minus 12, it's not the number that matters, it's the sign. So 1 minus 12 is negative. It's -11, but it's negative, right? So if I look at the graph of this equation, this one was y equals 3x squared. And then, oops, my mouse went away there, plus x, and then plus 1. Okay, so if I graph this one, I will see that there are no x-intercepts. Not surprising because the discriminant is negative and that negative is inside of a radical, so my answers are complex. Okay, so there are two solutions. Let me even add that bit right here. So this one has two x-intercepts and it has two real solutions. This one has no x-intercepts, but it has two complex solutions. Don't know what they are yet, but it has two complex solutions. I think we'll find them soon. All right. Then on the next page, we got one more we want the discriminant for. So b squared minus 4ac is, okay, 2 squared minus 4 times 2 times 1. That's 4 minus 4, that's 0. 0 is neither positive nor negative. So if I graph this one, I'm going to have the x squared, let's see, plus 2x plus 1. So it has just the one x-intercept. And one real solution. The reason it only has one x-intercept is because in the quadratic formula, this is the thing that you're going to add and subtract. So if you take negative b plus 0 or minus 0, you're not changing the first part of it because you're adding and subtracting 0. It stays the same. You only get one answer. Okay, so number 6, it says, if the graph has exactly one x-intercept, what are the number and type real or complex solutions? So if it has one x-intercept, it has one real solution. Okay, as we noted up there, that's what it would mean if it has one x-intercept, because there is a real solution. So there's not always two solutions, or I should say not always two distinct solutions. When there's an x-intercept, the solution is called a solution of multiplicity 2, so the same solution happens twice is what it really means. So there's only one distinct thing that is happening, one distinct solution. There are no real solutions. I misspoke. No complex that are not real. Nothing imaginary. Just the one real solution occurring twice. Okay. So, number and types of solutions. If the discriminant is positive, then there are two real solutions, which means two x-intercepts. If it is 0, there is one real solution, which means there is one x-intercept. If it is negative, it means that there are two complex solutions. And there are no x-intercepts. Evaluate the discriminant for each of the following. Indicate the type and number of solutions. All right, let's do it. So the discriminant, b squared minus 4ac for all of these. All right, so for the first one, we've got negative 7 squared minus 4 times 2 times negative 4. Okay, it wants us to actually evaluate not just the sign, and that's because we're going to do part B or actually get the solutions in a little bit, so why not get the whole discriminant right now? So negative 7 squared minus 4 times 2 times negative 4. So this is 81. And indicate the number and type of solutions. There's going to be two real solutions because that's a positive number. All right, do it again. All right, so we're going to have 1 as b squared minus 4 times 3 times 1. Okay, so for the next one, 1 squared minus 4 times 1 times 1, negative 3. No, I forgot the 3 there. My A was 3, and I wrote it down correctly here. Negative 11. There we go. Negative 11. And so this means that we're going to have two complex solutions. Okay. All right, we do it again. So we'll have negative 2 squared minus 4 times 1 times 1. 0. So this one's going to have one real solution. And our last one. Oh, they're trying to trick me because I'm not equal to 0, so I have to add the 1 over first to get it equal to 0. So I've got 3x squared plus 2x plus 1 equals 0, and I do that before I identify a, b, and c. So now I can do b is 2 squared minus 4 times a, which is 3, times c, which is 1. And I get 2 squared minus 4 times 3 times 1, which is negative 8. And so I know that I'm going to have two complex solutions. Okay, so keep these discriminants in mind because when we go to the next page, we're going to solve each of the equations fully. And so we're just going to pop the discriminants in instead of recalculating them because we've already done all the work here. Okay, let me get my decimals off the way. Okay, so we're planning to use the quadratic formula. The x equals negative b plus or minus the square root of b squared minus 4ac over 2a. And on the previous page, we've already done the inside of the radical piece, the discriminant piece. We just need to do the rest of it. Okay, so on the first one, b was negative 7. So we're going to have x equals negative 7 plus or minus the square root of. Our discriminant was 81. And then we're going to have over 2 times a, so 2 times 2. All right. So this is going to be, I'm sorry, it was negative 7. Negative b, and b was negative 7, so negative 7 right there. So I'm going to have 7 plus or minus 81 is a number whose square root comes out exactly as 9. So I'm going to do the square root of 9 here, and then over the 4. Now, because 7 and 9 are like terms, we're just going to take 7 plus 9 and 7 minus 9, divide it by 4, and see what we get. So we're going to add those up. We're going to combine them. So 7 plus 9 divided by 4, and 7 minus 9 divided by 4, and we get the answers 4 and negative 1/2. So x equals 4, and x equals negative 1/2. So those are my two answers for the first one. Okay, on to the next one. The b value is 1. So x equals negative 1, negative b, I almost forgot to write that little bitty negative there, plus or minus the square root of, my discriminant is negative 11, over 2 times a, which is 3. Okay, so I have negative 1 plus or minus, I have a negative inside my radical, so I need to separate this into the square root of 11 times I, and then over 6. Now, I also need to get this in a plus bi form. And in this form, the 6, which is underneath both parts currently, needs to be distributed. So we're going to separate this into x equals, I'm going to write them both separately for now. So x equals negative 1/6 plus the square root of 11 I over 6, and x equals negative 1/6 minus the square root of 11 I over 6. I'm writing them separate because that's the way that my math lab is going to want you to enter them, the two answers separated by the comma. Sometimes for shorthand, we would just write negative 1/6 plus or minus the square root of 11I over 6. That would be the two together, but they are separate numbers. One of them is negative 1/6 plus the square root of 11I over 6, and the other one is negative 1/6 minus the square root of 11I over 6. Okay, so our last two, starting with, I'm going to switch colors just to help break it up a little bit. Okay, so the b value here is negative 2. So we're going to have negative 2 plus or minus the square root of, our discriminant was 0. And then we'll have over 2 times 1. So that's 2 plus or minus 0 over 2. And 2 plus 0, 2 minus 0, they're both 2. So this whole thing is 2 over 2. So x equals 1. Like we said, there was going to be one real solution there. Okay, and the last one, it's supposed to give us two complex solutions. So let's see. We're going to get our x equals negative 2 plus or minus the square root of, our discriminant already came out as negative 8, over 2 times 3. Okay, so we have negative 2 plus or minus the square root of 8I so far over 6. This is not done. So first thing was to take this negative out, not inside the radical, but out past the radical as an I. Then I think 8, there's a perfect square, namely 4 that goes into 8. So I've got to keep breaking this down. So I've got negative 2 plus or minus the square root of 4 times 2I over 6. The square root of 4 is 2, so negative 2 plus or minus 2 square root of 2I, right? The square root of 4 is 2, so that came out outside the radical. The square root of 2 I could not evaluate, so I left that in, then over 6. Now, I need to separate and reduce this fraction. I'm going to reduce it first. I'm going to reduce everything, the coefficients. I cannot reduce early when there's no number in front of the second part because this 6 needs to distribute. Maybe we should distribute it first just to make sure. So I'm going to distribute this 6. So that's negative 2/6 plus or minus 2 square root of 2I over a 6. Now, both fractions have to reduce. So I have negative 1/3 plus or minus the square root of 2I over 3. It would not do to reduce just those two and not this one. I have to reduce them both. I have to distribute and reduce. Okay, and then we have to write our two answers separately. So one of them is negative 1/3 plus the square root of 2I over 3, and the other one is negative 1/3 minus the square root of 2I over 3. And then I have my answers. That was a lot for this one because I had a lot of steps, a lot of things to do. I had a negative radicand, negative number inside the radical, so I had to pull out the imaginary component, and it also was a number that had a perfect square factor in it, so I could break it down. And then I had fractions I could reduce, and then I could separate them and get my final answer.